Welcome! In this elementary calculus tutorial, we are going to do integration by substitution. And so I'll show you how I do problems like these. So let's begin with question 1, where we're asked to integrate 3x squared times x to the power of 3 minus 2 all to the power of 6 with respect to x. Okay, and so you look at this. What is the most complicated part of this? Well, it's this part, getting 6th powered. And the inside function is what we want to let to be u. And so over here in my scratch paper section of the page, let's say let u equal x cubed minus 2. All right, now with that, we want to take the first derivative, du on dx, and so it's equal to 3x squared. Right, and now what we do is a little bit of algebra in our head, pretending for a moment that this du on dx is a fraction, although it's not. But it behaves much like it in the sense that when we do this algebra, we will find a substitution or a way to replace dx. Okay, so taking the dx over, taking the 3x squared under, and swapping sides, we will see that we have dx can be replaced with, by substitution, du over 3x squared. And so this is what we do in this integral. Okay, and so what was u? It was x cubed minus 2. So we have 3x squared, u to the 6th with respect to x. But then this says that we can replace dx with du over x cubed, or 3x squared. So we have 3x squared, u to the 6th, du over 3x squared. All right, now the magic happens because we can cancel the 3x squared in the top and the bottom, and we just end up with an integral that has u's in it, which is exactly what we want. So this integral will work out nicely by substitution. Okay, now this is just a polynomial, and so we can just add 1 to the exponent and divide by the new exponent. So we have u to the power of 7, and then dividing this by 7, and we need to add the c. Okay, now what was u? It's x cubed minus 2, so we need to fill that back in. Okay, that's an x cubed minus 2 to the power of 7, and then plus c. Okay, so this is how we do it, and I'm ready for the next problem. I don't know about you. So question 2. Calculate 8 sine to the power of 1/3 x times cos x with respect to x. Okay, we've got to integrate this. Now, this is the tricky one here, the sine to the power of 1/3. So that's the hint. We should let u be equal to sine x. All right, so given that, we want to take du on dx. Differentiating sine, remember we get cos. Okay, let's do our little algebra trick. So we're going to replace dx with du over cos of u in our substitution. So this then is equal to 8 u to the power of 1/3 cos u, or sorry, cos x. And then the dx can get replaced with du over cos x. Now this should be cos x down here as well. Okay, and so we can now see that we can cancel the cos x, and we just have an integral of 8 u to the 1/3 with respect to u. And so it only has u's in it and numbers. That's awesome because now it's easy to do. So we have a power, and we add 1 to the exponent, divide by our new exponent. So 1/3 plus 1 is 4/3. And then we need to divide by 4/3 our new exponent and add c. All right, so now that we have this, we're almost done. So now we just need to simplify and plug back in what u was in terms of x. So we have, let's see, 8 over 4 is 2. So what I'm doing here is I'm multiplying top and bottom by 3/4, right? So if I set this out, this is 3/4 times 8, and then u is sine x, but it's to the power 4/3. Okay, so let's simplify the fraction out. 8 over 4 is 2. 2 times 3 is 6. So we have 6 sine to the 4/3 of x, and then plus c. All right, so let's just double check here with Mathematica, because this is a tricky one. So I will enter in here 8 sine of x. And now I want to take that to the power of 1/3. And then multiply by cos of x. Okay, integrating with respect to x, what do we get? 6 sine x to the power of 4/3. And that's exactly what we have here. Now remember, Mathematica leaves off the plus c, but you shouldn't, because it should be there. All right, let's move on now to question 3, and I'll scroll up a little. So question 3 says, calculate the integral 4 minus 9x with respect to x. Okay, and so knowing a little bit how this is going to work out, we're going to have something like 1 over u, but I would prefer that the coefficient there be positive. So just so you know, you can swap this around if you insert a minus in the top. And so we would have minus the integral of 1 over 9x minus 4. In other words, just multiplying throughout by minus 1. If you bring it back in, this is what you'll get. Okay, so now I want to so let's do this out of the way here. Let u be equal to 9x minus 4. Okay, let's take the derivative, du on dx. And so we get 9. Let's do our little algebraic trick. dx, we're going to replace that with du over 9. Okay, so here then we have minus the integral of 1 over u dx, but we can replace the dx with du over 9. Okay, now this is a constant. We can pull this out the front. And so we have minus 1/9 times the integral of u to the minus 1 du. And now we can just finish this off. The integral of this is natural logarithm of u. So minus 1/9 ln, or log to base e, or just log, all right, for your sake, ln of u. But remember, u is 9x minus 4. And then we have our plus c. Okay, let's move on to question 4. Where we have a definite integral, minus 1 to 3, 8x cubed over x to the power 4 plus 1. This is integrated with respect to x. All right, now let's look at the structure of this thing. So the derivative of that denominator is a constant times the numerator. So this tells us then that if we let u be equal to the denominator, that an integral by substitution will work out nicely for this. So here, let's say let u be equal to x to the 4th plus 1. Now let's take the first derivative, du on dx is 4x cubed. Okay, so you see these are off by a constant, multiple of 2. And so now we're going to replace dx with du over 4x cubed in here. Okay, so let's continue. Now I'll start by leaving off these numbers, right? Because I'm going to make a substitution here. So we have 8x to the power of 3 over u, and then with respect to u, replacing the dx with du over 4 x cubed. But now it's with respect to u, and so as soon as I do that, I need to change these bounds of integration here. Okay, so let's note u as a function of x is x to the fourth plus 1, but u as a function of minus 1 is minus 1 to the power of 4 and then plus 1, and so this is 1 plus 1, which is 2. So then down the bottom, this is u equals 2. You can leave it off if you like, but I think it's a good idea to put it in here, at least in one of these, so you're reminded that you're subbing in a u value rather than an x value. All right, let's do the same thing for the top. 3, so u of 3 is 3 to the power of 4 and then plus 1. Okay, so 3 to the power of 4 is 9 to the power of 2. 9 to the power of 2 is 81, so we have 82 here. So let's put 82 at the top. Okay, and now let's simplify all of this. So 8x cubed over 4x cubed is 2. We can bring our 2 out the front. And then we have the integral of u to the minus 1 with respect to u. And so we get the natural log of u. So 2 ln of u. I'm putting a square bracket here because I'm going to sub in u equals 2 and u equals 82 and take a difference. Okay, so what we need to do now is put those numbers in. So we have ln of 82 minus ln of 2. And now we need to use a log rule to simplify this, or we don't have to, but it's a good idea. So the log rule says that if we have a difference of 2 logs, we can represent that as a log of a quotient. All right, so 2 ln of 82 over 2. Now what's half of 82? Isn't it 41? Okay, so twice natural log of 41. All right, now let's just double check this with Mathematica. So 8x to the power of 3 over, in brackets, x to the power of 4 plus 1. We're integrating with respect to x, but this is a definite integral, so I need to include the bounds of integration. So I'm entering minus 1 and 3. Okay, so why is this different to what I've got? Well, 41 squared is probably 1681. Remember, there's a log rule that says that I can bring this number out the front. Now, I think this looks better to me. Maybe it's a matter of personal taste. So we've got 41 to the power of 2 via a log rule, but let's just check what 41 squared is. Okay, 1681. So these agree. All right, fantastic. Let's move on to question 5. Where we're asked to integrate something with the v's in it. It's a fraction. Now immediately, don't be fooled to think that you need the quotient rule, because you can simplify this. The v squared can go into this and into this. And so we can write this as the integral of 3 minus 2 v to the minus 1. Okay, so we can simplify it just like this. Now we can break up this integral if we really want to. We can write it as the integral of 3 with respect to v minus twice the integral of v to the minus 1 with respect to v, if we want to, or we can just look at this and decide what the integral is. All right, so what we have then is 3v and then minus 2 natural log of v, and we need a plus c. Okay, fantastic. Let's move on to question 6. Now, I think I'm going to want more paper for this, so I'm going to toss this one on the floor and use it for something else later. All right, so we're up to question 6 here. Calculate the integral of x e to the minus x squared with respect to x. All right, so just a mental note, the derivative of x squared is 2x. And so we want to let u be equal to the exponent here. So let u be equal to minus x squared. Okay, so then du on dx is minus 2x. And so we can then replace dx with du over minus 2x in here. So x e to the power of u, because u is minus x squared. We're replacing dx with du over minus 2x. Okay, let's simplify. We can see that we can cancel an x. Let's bring out the minus a half out the front. And now suddenly it becomes really easy. So the integral of e to the u with respect to u is e to the u. But u is equal to minus x squared. And then we need a plus c. All right, great. Let's move on to question 7. Calculate a definite integral from 1 to 3 of 3 e to the 2x times e to the minus 2x minus 1 with respect to x. All right, now let's have a look at the structure of this thing. What happens when we expand this? If we were to expand this, we can see that these two terms would cancel and we would have fewer things to worry about. So that looks like a good idea. So I'm going to write this as 3 times the integral from 1 to 3 of the expanded part of these two. And so these give us 1, and then we have minus e to the 2x. Okay, so the product of these is 1. The product of this and this is minus e to the 2x. And now, since we need to think about this as the derivative of e to the u with respect to u is e to the u, we want to let u be equal to 2x. Okay, now differentiating this, u on dx is just 2, and so we can replace dx with u over 2. Okay, so let's go ahead and do this. We have 3 times the integral. I'll leave off the bounds for now because we'll change this in terms of u. We have 1 minus e to the u, because u is 2x as we set out. And now we want to replace the dx with du over 2. Okay, great. Now, what is this in terms of u? Well, u of 1 is 2 times 1, which is 2, and u of 3 is 2 times 3, which is 6. Okay, and so then we have new bounds from 2 to 6. And remember, this is in terms of u, so if you want to add in u equals 2, that's no big deal. All right. So let's finish this off. So we need to do this with a bracket around all of this. Okay, and so let's bring out the 1/2. So we have 3 over 2 integral from 2 to 6, 1 minus e to the u with respect to u. And now integrating this, we have the integral of 1 with respect to u is just u. The integral of e to the u with respect to u is e to the u. I put in now a square bracket with the bounds written on this side because next we're going to sub those bounds in. Okay, so subbing in the 6, we have 6 minus e to the power of 6, and then we are subtracting 2 minus e to the power of 2. So now we need to simplify this. Okay, 6 minus 2 is 4. Then we have two minuses here, which gives us a plus. So let's put that first. So e to the power of 2 and then minus e to the power of 6. And this is what we have. Okay, let's get Mathematica to double check this. So we're integrating 3 e to the power. It's easier to write exp here, incidentally. So exp2 space x, and then let's put in our bracket exp minus 2x, and then subtract 1. Nope, outside there. Subtract the 1. Okay, now our bounds of integration here are from +1 to +3. I think I've got that written correctly. Okay, let's run this. And it looks a little bit different to what we have. So what we can do now is expand and then factor, or just plain factor, and that should probably do the job. Okay, so I can see it's almost like what we have here. Now, Mathematica has pulled out an extra minus, but if you just put that back in, then you have exactly what we have. All right, let's move on to question 8. Where we calculate the integral of 4 sine of 2 minus x with respect to x. Now, clearly here, you want to let u be equal to 2 minus x. Okay, differentiating the u on dx is just minus 1. So then we can replace dx with du over minus 1 or minus du. So let's go ahead and do this. Pull the 4 out the front. So we have sine of u, and then we're replacing dx with minus du. So let's put the minus out here. Okay, so this is easy now, isn't it? The integral of sine is minus cos, because the derivative of minus cos is sine. So we have minus 4 times minus cos of u, and then plus c. Okay, so then we have minus times minus gives us plus, so 4 cos of u, but u is 2 minus x, and then we have our plus c. So that should be it. Let's get Mathematica to check this. So 4 sine of 2 minus x, and then we're just integrating this as an indefinite integral. Okay, now I can see that Mathematica has used an angle addition formula for this one. So even though it looks different, it should be the same thing. All right. So what you can do is you can go and remember the angle addition formula or look it up. Or what you can do here is give this a value. Let's see. So x equals, say, 3.5, for example, and then enter the other function and see if those give you the same numerical value. I mean, that's not proof that these are the same, but does help you at least believe that they are the same. Okay, so we got the same number here, so these should be the same thing. Of course, it's not proof, but it gives you some confidence that you have the right answer. All right, I better clear the X. And let's move on to question 9. Okay, so in question 9, we are integrating from 0.5, and I'm just going to write a half here to 1. Okay, then we have x squared cot. Remember, cot was the inverse, multiplicative inverse of tan. So cot is cos over sine. Okay, so it looks like we might need multiple substitutions in this one. So first, let's let u be equal to what's inside here, x cubed. And incidentally, the derivative is a lot like this, right? Which tells you this is going to work out nicely. So take du on dx. and we get 3x squared. Now do our little algebraic trick. We're going to replace dx with du over 3x squared in here, but we also need to know our new bounds of integration. So u as a function of 1/2 is 1/2 cubed, or 1 over 2 to the power of 3. 2 to the power of 3 is 8. So we have 1/8 for that. U of 1 is 1 cubed, which is 1. And so our integral is the integral from 1/8 to 1 x squared cot of u, and then we have du over 3x squared. Great, so now we can cancel the x in numerator and denominator, bring out the 1/3. And so we have an integral of a cot function. Now, what you can do is you can look up what this is, but that's kind of a lazy thing to do when you can really calculate what the integral of cot is. So let's rewrite this. It's cos of u over sine of u. Okay, and now let's see. Is the derivative of the denominator like the numerator, or a constant multiple of it? And the answer is yes, it is. So let's let v be equal to sine of u. Let's differentiate v. So dv on du is cos of u. Now, our substitution would then be replacing du with dv over cos of u. So let's go ahead and do this. So we have 1/3, a definite integral. We'll leave the numbers off for now because they're going to change as soon as we have this in terms of dv. So now we have cos of u over v. V was sine of u. And then we have replacing du with dv over cos of u. Okay, magically the cos of u's cancel, which is how we planned for this to go down anyway. And now what are the new values on our bounds? Well, we need to calculate this here. So u of 1/8 is sine of 1/8. We can put that here, sine 1 over 8, and u of 1 is sine of 1. So that's the top there, sine of 1. Okay, great. Now, let's simplify this integral and calculate it. So we can cancel the cos u's. And when we do, we've got v to the minus 1 integrated with respect to v. Okay, we are nearly there. Now the integral of v to the minus 1 with respect to v is the natural log of v. So 1/3 ln of v and then this is from sine 1/8 to sine of 1. Okay, so now when we sub these in, we sub this in, we sub this in, we take a difference, but remember there's a log rule that we can use. But first I will write this down. So ln of sine of 1 minus ln sine of 1/8. Okay, and then now let's use our log rule that says that this is a log of a quotient. So we have 1/3 natural logarithm of the quotient sine of 1 over sine of 1/8. And I'm struggling to fit this in here. I hope you can read it. but I'm writing 1/3 ln sine of 1 over sine of 1/8. All right, and so let's get a numerical value of that also. So 1 over 3.0. This will make sure it comes out numerical. And then I'll just write log. This will be understood by Mathematica as the natural log. And then we'll enter our quotient, sine of 1.0 over sine of 1.0 over 8. Okay, and so I get something like approximately 0.6364 or 65 if I round to 4 decimal places. Okay, now just to double check, let's get Mathematica to integrate this thing. As it was originally stated, so x goes from 0.5 to 1, and I do hope they're the same. No, did I leave off? I must have left off. What did I do? X squared, no, okay, I put cos rather than cot. There we go. Okay, good. Now that's the same thing as what we got there. So 0.6364 when we change that to cot as it should have said. All right, fantastic. Let's move on to question 10. So in question 10, we are integrating sine x cos to the power of 5 times x dx. Now, I hope for you it's getting obvious now what to let u equal to. So here, let's let u be equal to cos of x. Okay, and so we differentiate du on dx is minus sine of x. So then we're replacing dx with minus du over sine x in here. Okay, so this then is the integral of sine x times u to the power of 5 times minus du over sine x. Okay, and so let's simplify this. We can see that we can cancel the signs. So minus integral of u to the 5th with respect to u. So now we add 1 to our exponent. We get u to the power of 6. We divide by our new exponent, 6, and we add c. Now u is cos. So we have minus 1/6 cos to the power of 6 x and then plus c. Okay, moving on to question 11. Calculate the integral x sine of 2x dx. All right, so here we want to let, you know what, this is no longer an integral by substitution, and I can see that here because this derivative of 2x is not related to x. We're just going to get a constant here. So this looks like for these, we want to instead set out integration by parts. Okay, so what I'm going to do is recall how this comes about. Now, similar to the product rule of differentiation, whoops, I should write equals v du plus u dv. Okay, and then we take 1 over to the other side. So v du is duv minus u dv. Something like this. Okay, so here's our integration by parts formula. And so can we view this in that way? Now, I choose the one whose derivative can cycle around. All right, and so let's replace sine by a derivative. So we do that by integrating sine of 2x. All right, so the integral of sine of 2x with respect to x is minus cos of 2x multiplied by 1/2, because if you differentiate this via the chain rule, it would generate an extra 2 out the front. So you need to compensate for that with the 1/2. Okay, and so now we want to turn this, let's say, so we bring out our minus 1/2 here, x, and then this is the derivative of cos of 2x. Okay, so just to check what I've done, I have replaced this with a derivative. Okay, and so if you actually differentiate this, you would bring out an extra 2 using the chain rule. So you would get minus 2 sine of 2x. Okay, and so that's what the minus 1/2 does. It makes those cancel. All right, so now what we see then is via substitution, we have minus 1/2, the integral of x with respect to cos of 2x. Okay, and so we now want to associate it with what we have here, the integration by parts formula. So we have this is going to be our v, and this in here is going to be our u. So we can now rewrite this minus 1/2 integral of, okay, how do I want to write this? Let's just put a big bracket around that. So integral of 1 duv and then swap these, putting these the other way around. I should put a little bracket around these two. Okay, so then we have the integral of cos of 2x with respect to v, the dx. Then I end my big bracket there. Okay, so next, this integral is clearly just x cos of 2x. And then bringing this minus 1/2 in, we have plus 1/2 times the integral of cos of 2x with respect to x. Okay, so we're almost done. Now this integral should be somewhat easy, right? So the derivative of sine is cos. So this is sine of 2x times something. So we have plus sine of 2x. Okay, I've just left some space here because I'm going to think about what the derivative of this is with respect to x. So I would bring out an extra 2. Right now, to make this work, I need to have a 1/4 here. Okay, so if we differentiate this, we bring out the extra 2, cancel that, and we get a 1/2. So here's our integral, and we're now done. So this was integration by parts. Okay, so now let's move on to question 12. And this also looks like integration by parts. And so we had v du integrated is uv minus the integral of u dv. All right, so here's our integration by parts formula. Now we need to identify what to call what. So the one whose derivative cycles around to itself eventually is e to the x. So we now want to write this in terms of a derivative. So we just have 3x times the derivative with respect to x of e to the x. Remember, the derivative of e to the x with respect to x is e to the x. This is still with respect to x. Okay, now we can pretend like the dx's are canceling, but this is a substitution. So we have then 3 times the integral of x with respect to e to the x. And now let's say this is our v, and this inside here, the e to the x is our u. Okay, so now that we have that, let's apply our formula. So we have 3x e to the x minus 3 times the integral of e to the x with respect to x. So e to the x is the u, and the x is the v. Okay, so we're almost done here. The integral of e to the x is e to the x, so we have 3x e to the x minus 3 e to the x, and then plus c. Now we can tidy this up a little bit by factoring out the common e to the x. And there's a common 3 as well, isn't there? So 3 outside of x minus 1 e to the x, and then plus c. Okay, fantastic. Let's move on to question 13. All right, so in question 13, we have to integrate the natural log of s with respect to s. Okay, now this is one that should be done by integration by parts. So 1 is the derivative with respect to s of s. So we can write this as the integral of natural log of s ds on ds ds. Is that how it works? Yeah, but I didn't need to write that, did I? Okay, so let's remember what the formula is again. We've got v du. Integrated is uv minus the integral of u dv. Okay, so how can we view this in this context? Well, here we have a v, and here we have a u. All right, so we don't need this. Let's start again and say that this integral, according to this rule, we have the product of the two of those. So s ln of s, and then minus the other way around, s d ln of s. But we can perform a substitution introducing a ds in this. Integral of s d ln s with respect to s ds. All right, now what's the derivative of the natural log of s? Well, it should be 1 on s. All right, and because I sometimes forget this, I can just check. Okay, yes, that's right. It's 1 on s for this. So we have s ln s minus the integral of s times 1 on s with respect to s. Okay, the two of these will cancel. We have the integral of 1 with respect to s. And so then we get s ln s minus s and then plus c. And so you can factor out the common s. S ln s minus 1 and then plus c. Okay, is that right? So if I integrate this, yes, that's exactly what we get. And if we factor we would pull out the common s. Okay, question 14. We are asked to integrate x times the square root of x plus 1 with respect to x. And we want to do this via integration by parts. So what we do is we represent the square root of x plus 1 as a derivative. And so we have that it's the derivative with respect to x of 2/3 x plus 1 to the power of 3 over 2. Now, if you actually differentiate this, the 3/2 will come down and cancel that 2/3. And then we will multiply by the derivative of x plus 1 with respect to x, which is just 1. And remember, we subtract 1 from the exponent, we get a new exponent of 1/2. But x plus 1 to the power of 1/2 is the square root of x plus 1. Okay, so this does differentiate to give the square root of x plus 1. Okay, so now that we have this, let's pull out the 2/3. And simplify. So this is the integral of x with respect to x plus 1 to the power of 3 over 2. Okay, so now we can use integration by parts. So 2/3. Now we multiply the two of these. So x times x plus 1 to the power of 3 over 2. And we subtract the other way around in an integral. The integral of x plus 1 to the 3 over 2 dx. Okay, so now we just need to integrate this and simplify. Okay, so we add 1 to the exponent here, and we have x plus 1 to the 5 over 2. We divide by our new exponent, so 2/5. And this is okay since the derivative of x plus 1 with respect to x is just 1. We have this and then plus c. Now we've completed the integral, but we can tidy this up significantly. So we can pull out a 1/5 out of this. So let's pull out a 1/5, factor it out. So 2/3 times 1/5 is 2 over 15. And so if I pull it out of this, I have to put a 5 in front. Okay, so we can pull out another x to the power of 3/2 out of this because it's common in both of these terms. So 2 over 15 x plus 1 to the power of 3 over 2. And then what remains is 5x in this and 2 brackets x plus 1 in this, because x plus 1 to the 5 over 2 is x plus 1 to the 3 over 2 times x plus 1 to the 1. And then we need our plus c again. Okay, so we just need to simplify this inside the brackets here. So 5x minus 2x is 3x. We have 3x there and then minus 2. And then we still have plus c. Okay, so there's the integral done. Okay, question 15. This is a bit of a tricky one. We're integrating cos of the natural log of x with respect to x. So to do this, we want to use integration by parts again. And so we need to express this in terms of a derivative. So we have x cos natural log of x, and then we subtract x times the derivative with respect to x of cos of natural log of x. And so this is just our integration by parts formula. Okay, so here's a u, here's a v. This is u times v, and then we swap those around in their position. Okay, but we can introduce a dx here and express it in this way. Okay, so now let's simplify this by differentiating cos of natural log. Now we need to use the chain rule to do that. The derivative of cos is minus sine. Okay, so I'll first rewrite this, x cos natural log of x. And then we have differentiating this, we have minus sine of natural log of x times the derivative of that inside function by the chain rule. Now the derivative of natural log of x with respect to x is 1 on x. So we have this. Now we just need to simplify this one. There are two minus signs, and we can cancel an x. So plus the integral of sine of natural log of x with respect to x. Okay, so now you're looking at this and saying, hey, hang on, how does this help us, Sam? Well, because, I mean, it's just as bad as this one, but you can apply the same trick again and then do some algebra. And that's what we will do to finish this off. So let's apply the same trick again. Okay, so then we have rewriting this cos natural log of x. And then we have plus the product of this and this is x sine of natural log of x. And then we subtract the other way around. So x d this, but we can express this as the derivative of sine of natural log of x with respect to x, and then put dx here. Okay, and so now we need to differentiate sine of natural log of x. So again, using the chain rule, now the derivative of sine gives cos. So we have minus x cos of natural log of x. And the derivative of natural log of x with respect to x is 1 on x. Okay, so we have this, and so we simplify this, and we'll see, oh, we have this over here. All right, and so let's do that. X cos natural log of x, and then x sine of natural log of x minus the integral of cos of natural log of x. Okay, so this is the same thing as this, right? So now let's just do some algebra to find out what this is by adding it to both sides. So 2 times the integral of cos of natural log of x is x cos of natural log of x plus x sine of natural log of x. And now we can just divide throughout by 2 and we get our answer. All right, now we do need a plus c here at this point. Okay, and so now let's divide by 2. So we see then that the integral of cos of natural log of x is 1/2 x outside of the sum of cos ln x plus sine of ln x and plus c. Okay, thank you.